So before we get started with our note for related rates, I want to go over derivative notations. So before we were using the prime notation, so let's say I got y is equal to x squared, or if I want to derive it, then we would just use a notation of, oh, we're going to do y prime, and then we would derive what's on the right side, so that'll become just 2x. But then the other notation was, instead of doing the little prime notation, we said, well, we have to do the d over dx notation. So this is showing that we are going to differentiate everything with respect to x, meaning x is our variable. So if I want to derive this, the notation would look like this. So this part is actually not necessary, but I'm putting it so that you can see that, okay, I'm going to derive both sides, the left and the right side, with respect to x. So if I were to distribute this into both of these, then I'll be left with dy over dx. And then I have d over dx of x squared. And I would have to derive this. So I have dy over dx is equal to, so first I need to derive this. We got 2 and then x. And then we derived everything with respect to x. So this will be my final answer for deriving the equation. Now, we derived everything with respect to x, and the reason why this notation is important is because we are showing that x is our variable. We are going to derive everything with respect to x, but then what happens if we're not deriving everything with respect to x? So this goes into implicit differentiation, which was actually the previous lesson. But I'm just going to briefly go over what you need to know from implicit and how it works. So implicit is like, well, what if I want to take the same equation, and instead of deriving with respect to x, I pick another letter that I want to derive it. So now this letter is not in here, but then let's say, so y and x are variables. But then the letter that I wanted to derive it with respect to is going to be the letter t. So I want to derive everything with respect to t. So I'm going to rewrite this part, but instead of x, I'm going to put in a t. So I want to derive everything with respect to t. And so first, let's go ahead and distribute each one. So the first part is going to be dy over dt. And then the second part is going to be d over dt and then x squared. Now we still need to derive this, but then this time t is not our variable in here, because before we had x and x, but then this time it's not. So when we derive this is implicit differentiation. So it's going to look like this. So first you're going to derive this the same way. But then instead of just finishing it off, because here we didn't have anything else, but implicit means that we have to add another dx over dt. So x is the variable that we derived, but then we derived everything with respect to t. Okay, so that's what you need to know before we start related rates. Because instead of just having two different variables of just x and y, we're going to introduce another variable. And you're going to see how that's important. Okay, so let's look at the first question. When a raindrop falls into a still puddle, it ripples out in the circles where the point, from the point where the raindrop hits. It says the radii, so just one radius, of the circles grow at the rate of 3 centimeters per second. So when we first read this question, we have to know what are our variables and how can we change this question into equations so that we can work with equations. So first we know that it's going to, so first let's just draw a picture of what's happening. We're going to have a raindrop that's going to fall. And then what this is going to become is it's going to go out in a circle. And then maybe like one other second later, it's going to have another larger circle that's bigger. Okay, so it's going to keep on going outside, but then there's a special, I guess, a certain rate that the circle is going to spread by. And the radius of the circle. So first we have the radius, so whatever measurement that is, and then maybe 1 second later, now this is going to be your new radius. And then from this radius, well, how fast is this growing? And they tell us what that rate is. They said it's going to be 3 centimeters per second. So it says the radii of the circles will grow. So every second it's going to grow. The radius is going to grow. So this means that if I have dr over dt, so I'm picking this because we have our radius that's growing per time. And I always look at the units to help me determine, well, what goes at the top and what goes at the bottom. Centimeters is from the radius and second is for the time. So the radius goes at the top and then the time goes at the bottom. So dr over dt, that's going to be my rate. So that's going to be 3 centimeters per second. And it says it grows at this rate, so meaning this value is going to be a positive number, but I'm not going to bother putting the positive because 3 already means it's positive. Okay, so that's what's given in the question. And A says find the rate of increase of the circumference of the circle. So again, it's asking you to find the rate, but the question tells us how fast the radius is increasing, but then this time we want to know, well, how fast is the circumference growing? So not this measurement, but then this measurement. So the length of the outside of the circle. So what they're asking you here is, what is dc over dt? Because we know that it is still a rate that's growing per time. So t goes at the bottom, but instead of a radius, they're now asking for a circumference. So this is what they're asking for. So we are trying to find, well, what is dc over dt? And that's all the information that's given. We know how fast the radius is growing, but you'll notice that if the radius increases, then the circumference will also increase, so they are related. And your job is to know how are they related. So how are C and R related? So we know that to get the circumference of a circle, if we know the radius, then we can use our formula and get the circumference. So the equation for the circumference of the circle is C is equal to pi d, or diameter is twice of the radius, so C is equal to 2 pi r. Okay, and now we are looking for dc over dt, meaning I want to derive this with respect to t. So let's derive this equation with respect to t. And if I want to derive this, let's give the d over dt to each one. So I'm going to have dc over dt. Okay, so I already got my dc over dt, which is what they want. And now I got to derive this. So r here is our variable. 2 pi, they're both constants because they're values that don't change. So how do you derive this? So first you derive this normally as you're deriving the r. And if you have something like 2x, you just get rid of the x. So this is going to be 2 pi. But because these letters are not the same, now I gotta attach dr over dt. Okay. And we are looking for dc over dt, so we're looking for this, and we have to sub this part in. So I know my dr over dt, that's going to be 3. So I'm going to sub that in here. So dc over dt is going to be 2 pi times 3. So my dc over dt is going to be 6 pi. And the unit is going to be, it's measured in centimeters, so centimeters, but it's per second. Okay, so to find the rate of increase, and we know it's increasing because it's 6 pi is a positive number. Okay. So we can say, therefore, the circumference is increasing at 6 pi centimeters per second. Okay, now let's look at B. Find the rate of increase of the area of the circle. So now instead of the circumference, I want to know, well, how fast is the area increasing? That has an area of 81 pi. So in the beginning, the area of the circle is going to be small, but as we get larger, you'll notice that it increases at a faster rate each time. So when the area is 81 pi, then what is the rate of increase of the area at that moment? Okay, because when it's small, the area is going to increase at a very small rate, and the bigger it is, it's going to increase at a faster rate. So what are they looking for here? In mathematical terms, the rate of increase of the area is going to be dA over dt, because per time we want to know how fast the area is increasing. Okay, so this is what we're looking for. At area is equal to 81 pi. So when it's 81 pi, what is going to be my rate? Okay, and back to our question, we know that our rate of the radius is given, because that's going to increase at a constant rate, but then the area won't. But we can work with this. We can work with the radius and get our area. So just like how we related the C and the R together, how can we relate the A and the R together? So we can do that by finding the area of the circle. So the area of the circle is pi r squared. And this shows a relationship between A and R. And I'm looking for dA over dt, meaning I want to derive this equation with respect to t. So I want to do d over dt, and that's going to give me let me label this B. It's going to give me dA over dt. And now I gotta distribute this to this, so just derive this with respect to t. So first you derive this just as you normally would, so pi, and then bring down the 2, and then r, and then 2 minus 1 is 1. And then because they're not the same letters, we gotta do times dr over dt. Okay, and let's see, so this is what I'm looking for. I have dr over dt, so that's 3, but I don't have my r. But we can get our r. Okay, so we have our area, but I want to get my r, so I'm going to again use this formula. And so when the area is 81 pi, what is going to be my radius? So if I use a is equal to pi r squared, and I sub in 81 pi as my radius, and I'm going to solve for r. I'm going to isolate for r. So the 2 pi's will be gone, and then to get rid of the square root both sides, you get positive or negative 9, but radius can't be negative, so it's going to be a positive 9. That's going to be my radius, so I'm going to sub in all the values to get my dA over dt. I got pi, 2, and then 9. My dr over dt was 3 up here. And now I just multiply. So dA over dt. This will be 6 times 9, 54 pi. And the units will be, now it's area. Unit of the area is centimeters squared. And we used second for our time. So how fast is it increasing? So we know it's increasing because it's positive. I'm going to say therefore the area of the circle is increasing at a rate of 54 pi centimeters squared per second at area is equal to 81 pi centimeters squared. Okay, so that's question number 1. Let's go to question number 2. How fast is the side of a square shrinking when the length of the side is 2 and the area is decreasing at a rate of 0.25 meters squared per second. So let's see what kind of information we can extract from this question. So first they're asking for how fast is the side of a square shrinking. So first let's just get a visual sense of what's going on. We're going to have a square. And this is going to be shrinking, so it's going to go smaller and smaller. But we know if it's a square, then we know that the length and width is going to be the same. So I'm going to call both of them S for side. So let me, make that a little bit more clear. So how fast is the side of our square shrinking? So if they're asking how fast is it shrinking, then they're asking for the rate, because they're asking how fast. So if they're asking for like how fast or how slow something is going to change, then that's always asking for the rate. So here they're asking, well, how fast is the side changing? So our S is going to go at the top because this is what's changing, but it's changing every time, right? So every second. So it's going to be ds over ds. Oh, no, let's use t for time. So ds over dt. So this is what they're asking because we want to know how fast the side is changing. And they're telling us that the length of the side is 2. So when this is 2, so when S is equal to 2, what is going to be this rate? And they tell us one more information. The area is, they don't tell us the area, but they tell us how the rate of the area that is decreasing by. So this means that my dA over dt, right, because my area is shrinking, it's going to be 0.25, but because it's decreasing, it's now going to be a negative. Okay, so we have established what they're looking for and what kind of information is given to us. Now we want to find ds over dt. And how do I find that? Well, first I want to know, how do I relate these two together? So I know for the area of a square, that's going to be a is equal to s squared. And I'm looking for t at the bottom, or dt at the bottom. So that means I got to derive both with respect to t, d over dt. And my first one, so my a is going to become dA over dt. And we're going to derive this as you normally would, so 2s. And then because they're not the same letters, again, you're going to put ds over dt. And let's see, they are looking for ds over dt. So we're looking for this. And we have our dA over dt and we have our s. So let's sub it in and let's isolate for ds over dt. So we're going to have negative 0.25 and then 2 times 2 is equal to ds, not equals to, times ds over dt. Now, because these are multiplied, I'm going to divide both sides by 2 times 2, or 4. And I'm going to have ds over dt is equal to 1 over 4 divided by 4. Well, it's 1 over 4 times 4. It's going to be negative 1 over 16. So ds over dt is going to be negative 1 over 16, and the units for this would be, now s will be measured in meters, so not meters squared, but meters, because it's just the length, and it's going to change every second. So therefore, the side of a square is decreasing at a rate of negative, oh, well, I don't need to say negative because I already said it's decreasing, 1 over 16 meters per second. Okay. Now let's look at the next question. So if the length of a rectangle is increasing at a rate of 4 centimeters per second and the width is increasing at 5 centimeters per second, what is the rate of the area that is increasing when the length is 10 and the width is 12? So they tell us a bunch of information, but we know that it's going to be a rectangle that is increasing in size. Okay, so first let's draw a little visual so we know what's going on. So we have the length and we have the width. And let's take our given information and let's put that in a mathematical equation. So they said a length is increasing at a rate of 4 centimeters per second. So that means my L is going to be increasing every second, so per time. It's going to be positive 4. And my width, so my width is going to be changing at 5 meters per second. So, and they said, what is the rate? So at what rate is the area increasing? So they're asking for, well, what is going to be my dA over dt? Because they're asking for this when the length is 10 and the width is 12. Okay, so we have length and width, and we want to relate it to the area. So we know it's a rectangle, so what's a formula that relates L and W with the area? So we know that the formula for the area of a rectangle is length times the width. And we want everything derived with respect to t, because they're all divided by dt. So I'm going to have derive everything with respect to t. So my first one is going to become dA over dt. Now these are two variables that are being multiplied. And if they're being multiplied, when you derive them, you have to use the product rule. And if you recall what the product rule is, it's if you have f times g and you want to derive it, you get fg plus fg, derive the first and you derive the second. So we got L and W. So first I got to derive the L. So if I derive L, it just becomes 1. But because they're not the same letters, I got to do dl over dt. Okay, so that's this f prime portion. And then the g, so that's just the second one multiplied. And then you do the same thing with f and then g prime. So the first one stays as this, so L. And then derive this, so again 1 times, and then derive the w with respect to t. You're going to have dw over dt. And here we're looking for dA over dt, so that's what we're looking for. So let's keep that. And let's see if we know everything. We have our dl over dt, we have our w, and we have our length, and we have our dw over dt, so they tell us everything. So my dl over dt is 4, width is 12, length is 10, dw over dt was 5. So my dA over dt, that's 48 plus 50. 48 plus 50, that's 98. And my unit is, they use centimeters, so it's going to be centimeters squared. And time was every second, was per second. Okay, so therefore the area is increasing at a rate of 98 centimeters squared per second. Okay, so the next is a challenge question because it requires a little bit more steps compared to the ones that we did, but it relies on similar concepts. It's just you have to think a little bit more outside the box, but don't let the word challenge scare you. Okay, so we got a conical reservoir, so this means that we have a cone. So let's draw a little cone so we have a little sketch of what's going on. Every cone will have a circular bottom. We're going to have some sort of radius, and we're going to have some sort of a height, and we know this is going to be a 90-degree angle. So this is filling with water at a constant rate of 3 meters cubed per second, so this is a volume now. And The reservoir is 3 meters deep and has a diameter of 8 meters at the opening. So we can put that measurement in. So this is going to have 3 and the diameter is 8, but normally diameters are kind of useless, so I'm going to go with the radius. So the radius is, instead of 8, it's going to be half of that, so it's going to be 4. Determine the rate at which the depth of the water is increasing when the depth of the water is 2. Okay, so what's going on is we are filling it with water. Okay, and we know that the volume of this is changing at a constant rate. Okay, so we are filling 3 meters cubed every minute. So we have a kind of a graphical representation of what it looks like. First, let's take all these sentences and put it into mathematical equations. So we got a conical reservoir filling it at a constant rate of this. So we know that this is the volume. So the volume is changing every minute. So the letters that it's used for to represent this case is going to be dV, because that's our volume, over dt. And time is going to be measured in minutes. And this is going to be, we are filling it, okay, we're increasing, it's going to be a positive 3. Okay, and this tells us the information, so we already have that written down. So let's go to the next sentence. Determine the rate at which the depth of the water is increasing. So although it's 3 meters high and 4 meters wide, or 4 for the radius, when, let's say, the water is filled up like over here, this is going to have a different height and a different radius. Okay, so although 3 and 4 are fixed values, our volume depends on how much it's filled upside down, right? So this is how much it's filled, but at this point, it's not 3 meters. It's going to be less than 3 meters. And the radius at this point is going to be less than 4 meters. Okay, so let's say it's at some point being filled up, and I'm going to draw, well, let's say it's over here, and let's give this, because this is changing, okay, because as we fill up the cone, the height of the water is going to change, so let's give that a variable of h. And same thing with the radius. So the radius here is 4, but then down here is going to be a lot smaller. So let's say this is going to be our r. So we have 2 variables that are going to change, the radius and the height. And the question is asking, determine the rate at which the depth of the water is increasing. So we want to know, what is a change of h? Okay, what is the rate of h? So they're asking dh over dt. So that's what they're asking. When the depth of the water is 2. So not 3, when it's 2 meters high. So h is 2. So when h is, oh, not question mark. When h is 2, what is going to be my rate at which the height is increasing? Okay. And it's not going to be just 3, because this is in meters cubed. Okay, so that's how much the volume is changing, but that's not how the height is changing. Okay, and actually you'll realize that usually in the beginning, because here it's a lot more narrower, it's going to fit a lot more volume. Here it's going to increase at a faster rate compared to, like, let's say you're almost done with filling up the cone, because here you have a lot more volume to cover. So here it's going to increase at a fast rate, but up here it's going to still increase, but at a much slower rate than down here in the beginning. Okay, so we have laid out everything that we're looking for, okay, and everything that's given in the question. So we are looking for h, and we're given the v. So how can we relate the height and the volume together in one equation? So this is the volume of a cone, okay? So what is the volume, what is the equation for the volume of a cone? So I always draw this. So let's say I have this, this cylinder, and the cone, so if you had a full cylinder, the cone is always going to be a third of the volume of the cylinder. Okay, so I always, you know, I'm not a big fan of memorizing formulas. So I always say, well, if it's a cone, or even if it's like a pyramid, as long as it has a pointy top at the center, you always find the volume of the original shape, and then you always cut it into a third. And it's not just for circles, it's also for, like, if you have a pyramid. Okay, you would first find the volume of the rectangular prism, and then you cut that into a third, and then you get the volume of the pyramid. Okay, but I'm not going to go into detail right now. So let's get the equation for the volume of the cone. So the volume is going to be, so first, in order for you to find the equation of the cylinder, you first need to find the area of the base. So the area of a circle is going to be pi r squared, because it's going to be your r. And then I always think of it as, okay, you're going to take this shape and you're going to drag it all the way down. And then that is going to be our height. So I multiply by h. So that's the area of the cylinder. H, and then you have to cut it into a third because we're only interested in the cone. So we have our volume equation, and so we have our V and we have our H, but this equation has an extra variable of R. So I want to try to get rid of this R, and there is a way to do that, and I'm going to show you how you can relate the R and the H. So going back to this diagram, you'll notice that first we have the triangle of, so not just triangle, a right triangle, and the height is going to be 3, and the other length of the triangle is going to be 4. Okay, so let's say I just take this large triangle and I draw it here. So that's going to be 3, that's going to be 4. And let's say I'm interested in this one. So we use the letters R and H to represent the smaller triangle. So again, that's still right angled, and that's their height, and that's going to be my radius. And so there's multiple ways you can set up a relationship between R and H here. You can use similar triangles, or you can use the other ratio, which I personally like better. So you'll notice that they will both have the same angle. So let's say I have an angle of alpha. So that's an angle of alpha and that's an angle of alpha. I can come up with the ratio of this and this, and we can come up with the relationship. So my method of doing this is, well, this is my angle of reference. This is a right triangle, so I can use SOHCAHTOA. So that's my opposite, that's my adjacent. So if I use tan, so tan of alpha is going to be opposite over adjacent, so 4 over 3. So I can set up the same ratio for this little triangle using R and H. So it's going to be tan of theta, so not theta, alpha. It's going to be opposite over hypotenuse, so R over H. And these are the same. Okay, so whatever the angle is going to be, they're going to be the same. So I can actually take this and substitute it in here. So that's going to be R over H is equal to 4 over 3. And let's isolate from one of these, so 4 over 3H. And this is going to be how the radius and the height are going to be related. So I can use this relationship and sub that in here. So I can get rid of my two different variables. So I can only have H because that's what I'm interested in. I want R out of here. Sometimes you might want to keep it in there if the question has something to do with radius, but we don't care about that. Okay. Because like in the previous question, we had L and W and we had information of all of them. So we wanted to keep everything. But then this time we're only interested in H. So I want to try to come up with a relationship to get rid of the R. So let me sub in this equation so that I can have my volume equation without the variable of R. So R is 4 over 3H, and that's squared times H. Put that a little closer. All over 3. Now let's simplify this. So I got pi, I got 4 squared, and then H squared times H, all divided by 3 squared. So that's the 3 squared here, but let's have another 3. So it's going to be times 3. So in case you're confused, that's from that, and that is from that. So before I start deriving, let's simplify this a little bit more because we got H that's separated. So we got pi, let's do 16 pi, that's 4 squared, and then we got H cubed all over 3 cubed, which is 27. Okay, so now that we have our V and our H relationship equation and they're simplified, now we're going to find our what we're looking for. So remember, the question is asking for dV over dt. Sorry, the question gives us dV over dt. We're looking for dH over dt. So I want to derive this equation by d over dt because that's what's at the bottom. Okay, so I want to derive everything with respect to t. So this is going to be dV over dt, and now let's derive this. So this is this is a fractions, but it's actually quite simple because this is just a constant, right? There are no variables here. So let's derive this. So let's keep the constant, so 16 pi over 27, and derive this h cubed. So bring the 3 down. Let me put that at the top. And then times h squared. Okay, because we got to do minus 1. And then our last step, can't forget this because they're different variables, you got to add dH over dt. So I have derived this, and this is what we're looking for. And we have our dV over dt over here, and we have our h value. So all we have to do is just sub everything in and isolate for dH over dt. So my dV over dt is positive 3. Let's copy this down. So 16 times 3 pi over 27. And my h is 2. And dH over dt is what I'm looking for. Now let's put this to the other side by dividing. So we got 3, and we got 27 at the bottom. So I'm going to multiply this by 23. Divide everything by 16 times 3 times 4 pi is equal to dH over dt. Now let's see, I think I can cancel this out. And 27 is what I have at the top. 16 times 4, I get 64. And then pi at the bottom. That's equal to dH over dt. And the question's asking, what is dH over dt, or what is the rate of the depth of the water increasing at h is equal to 2? And this is what we have. And the units of this would be the height is in meters, and the time is in minutes. So we're going to say, therefore, the depth of the water is, now it's increasing because it's positive, so increasing at a rate of 27 over 64 pi meters per minute. Okay, so I don't think that was so bad. We just had to do an extra step of coming up with the relationship of the two variables, but it was pretty much based on the same things as we did above. Okay, so one more question. So So you should be able to do this, but I will, but you know, like, so I recommend you to try this yourself, but I will post a video anyway, so try it yourself, and then try to see if we got the same answers. So the top of a ladder rests against a vertical wall. If the bottom of the ladder rolls away from the base of the wall, how fast is the top of the top of the ladder sliding down? Okay, so let's just draw a picture of what's going on. We have a ladder that's sitting against the wall. So we have our wall, and it's sitting on the ground. And it's sitting on the ground. And let me draw the ladder. So that's the ladder. And this is going to be 5 meters, and the size of the ladder is not going to change. So I'm not going to give it a variable, I'm just going to say it's 5. And every time we have a wall or anything that's standing upright from the ground, it's always going to become a 90-degree angle. And we have the bottom of the ladder that's rolling away. So in this triangle, the bottom length is going to be increasing. Okay, so first let me give that a letter. I'm going to give that a letter of x, and it's going to be increasing at a rate of 1/3, so a third of a meter every second. And when that's going this way, they're asking, well, what is the rate when the top of the ladder is coming down? So this side of the triangle is going to shrink every second. So because this will also be changing, I'm going to give that a variable of y. So we got the length of x at the bottom and the length of y for the top. And so 5 is the hypotenuse, so I'm not going to give that a letter. And they say the bottom of the ladder is rolling away at a rate of 1/3 meters per second. So how can I convert that into a mathematical equation? So they're saying the change of x every second is going to be 1/3. So the change of x, so how do I represent that? So it's going to be dx over dt. So x is changing every time at 1/3 meters per second. And they're asking for how fast is the top sliding down. So they're asking for what is dy over dt when it is 3 meters above the base of the wall. So here they're telling us the y value. No, not a question mark. So when y is equal to 3, what is going to be the dy over dt? Okay, so now we have to try to relate the x and the y together. So I want to come up with a formula that shows the relationship between the x and the y. And we know that this part is going to be 5, and that's going to be fixed. So I'm going to use the Pythagorean theorem. So the Pythagorean theorem states that if I have x squared plus y squared, that's going to become the hypotenuse squared, which is 5 squared. And I want everything differentiated with respect to t. So I'm going to take this equation and I'm going to differentiate everything with respect to t. So first let's derive x squared. So derive this normally, so it's going to give me 2x, and I'm going to have to attach dx over dt. And then same thing with the y, I'm going to have 2y and then dy over dt. And then this is a constant, there's no variables here, so that's going to become a 0. So they're asking for what is dy over dt, okay, because that's what they're asking. So what is going to be this? We have our y value, we have our dx over dt value, we don't have our x value. But can we get our x value? Yes, we can, using this equation. So again, using this relationship, when y is 3, oh, forgot the square, what is going to be my x? Okay, so just isolate for x, 25 minus 9, so let's say 16. Oh, that's a square. And x is going to be plus or minus 4, but x can't be a negative value, so x is going to be 4. So we have our x value. So now we have everything, and we can isolate for what we're looking for. So I'm going to have my 2, and then my x value is a 4. Dx over dt, that's 1 over 3. Plus d2, and then y is my 3. And then they're asking for what's dy over dt. That's equal to 0. So let's isolate for this. So I have my 2 times 3 times dy over dt. And then let's bring this over to the other side, making it negative. So negative 2 times 4 over 3. Now let's divide both sides by 2 times 3. And I get dy over dt is equal to, cancel out the 2's, and I get negative 4 over 9. And we scroll down. And, well, first let me write down the units. So my length is in meters. And time is in seconds. So therefore, and the y represents the height. What did they use? Oh, the top of the ladder. So therefore, the top of the ladder is and oh, they say sliding down the wall. It's sliding down the wall, and we know it's sliding down because it's negative. It is sliding down the wall at a rate of 4 over 9 meters per second. And that's how you do related rates questions.